called price rearrangement could happen. For you can think about this, along two directions. One is, as we know, aluminum chloride is a very powerful Friedel-Crafts oscillation catalyst. So a catalyst can, speed up reaction. A powerful catalyst can, dramatically speed up reaction. So the adding of a catalyst can help bring the system into thermodynamic equilibrium. And what happens when the system is brought to a thermodynamic equilibrium means the more stable product will form as a major one. Okay? So these two guys, okay, this one is an O oscillation product, where there's no electronic communication between the carbonyl and the ring. And this is a C oscillation product. You have direct, the carbonyl group is conjugated with the ring, have a much better electronic communication. So this one is more stable. So adding aluminum chloride give you opportunity for a less stable one become a more stable one. This is just what happens when a thermodynamic equilibrium is established. You will have the most stable species, at the highest concentration. Okay? So out of these two, this guy is a lot more stable. So pretty much you're going to see only exclusively this guy, not this one. This is just consider stability. But also, I just showed you before the physics class break, you can think about mechanistically. This aluminum chloride is a powerful Lewis acid, so you can form a complex with this oxygen. Okay, and then here, yes, okay. So you form this complex, okay, and then this complex can undergo the ionization, give you the this ethylene cation and this the monoxide complex of aluminum chloride. Okay? So the ethylene cation act as a real electrophile, react with aromatic ring. So because of this still is this oxygen still is a activator and the OP director. So the ethylene cation will be connected. Mostly prefer the P side, but the P side is not available. It will connect to the O side. So eventually, will give you the rearrangement product. So that is the two ways to think about this the price rearrangement reaction. So just I would like to just give you one more example. Let's say. So first thing is you see the combination of O oscillation product and aluminum chloride. You immediately should trigger, okay, O oscillation product is a kinetic control product. You would like to rearrange to a more stable C oscillation product. And usually it won't happen, but now you are throwing aluminum chloride is a powerful catalyst, and it helps the system or bring the system to its thermodynamic equilibrium. So yeah, it can form its the more stable one. So then you can consider this one as electrophile to react with aromatic ring, and the this guy still is OP direct, okay? So you either want the electrified attack here, here, or here. But because the P side was already occupied, so you only can occupy, the O side. Okay, so that would, so the O side means the product will be, and keep in mind, will be a phenol product. So that is the rearrangement product. Am I recording it? Yeah, I think I am. All right. So the another example of thermodynamic control of the phenol reaction actually is a reaction of monoxide. Is basically is a carboxylation of the monoxide. So this reaction is actually still is being used to make aspirin. Another reaction is called Kolbe-Schmidt reaction. So the in this reaction, sodium phenoxide, its conjugate base of phenol, is treated by carbon dioxide at 125 Celsius degree and a very high pressure, 100 atmosphere pressure. And this reaction will lead to the C oscillation of the monoxide, give you sodium salicylate, and then you further protonate, it give you salicylic acid, and this guy, basically is the starting material for aspirin. So it's important to emphasize, the carbon dioxide, okay, is used at a high pressure and temperature. Especially temperature is pretty important. Why high temperature important? Because high temperature, it helps the reaction to reach, because high temperature speed up reaction. So it helps the reaction, to achieve its equilibrium. High pressure of carbon dioxide also helps speed up reaction. Again, helps the reaction to achieve its equilibrium. So this, the high pressure and the temperature, carbon dioxide high pressure and temperature is basically implies the reaction will happen near its equilibrium at least. Okay? So now let's think about the roles played by each reagent. So or each reactant. So you have monoxide, you have the carbon dioxide. These two things react. So the what you can see is the monoxide, okay, is a nucleophile. This guy is nucleophile. So its nucleophilicity, if I ask you, monoxide it's more nucleophilic than phenol or less nucleophilic than phenol. These two guys. Okay. Monoxide is a conjugate base of phenol. So which one is a better nucleophile? Monoxide. Okay. Very good, because of nucleophiles, they are electron pair donors. So the connecting charge only will dramatically enhance the ability to donate the electron pair. So if you just as a rule of thumb, a negative charge, okay, for the actual negative charge, you can enhance nucleophilicity by 10,000 times. Rule of thumb. In some cases, can enhance about 100,000 times, but average about 10,000 times. Yeah. So if you look at the nucleophilicity table, you have seen chapter 6. You probably you see some idea, because say alcohol nucleophilicity is 1, okay, alkoxide conjugate base of alcohol 10 to the fourth power, 10,000. Okay, and the carboxylic acid nucleophilicity is about 10 to minus 2. Carboxylate about 1,000, so 100,000 times greater. But anyway, the rule of thumb is if you put a negative charge on the nucleophile, it will be about 10,000 times more nucleophilic. So anyway, monoxide will be a lot more nucleophilic than phenol. Okay? And carbon dioxide, it's electrophile. And why it's electrophile? Look at the structure, you will see that. Because carbon dioxide is a molecule with two oxygen bound to the same carbon. So it's actually a very large amount of positive charge on the central carbon. But yet, carbon dioxide is considered as a very weak very weak electrophile. It's not strong one because of just think about it. Carbon dioxide, what's the shape of molecule? It's linear, right? So if you think about the nucleophile coming from, doesn't matter which side it's coming from, and the nucleophile are negative charged, and doesn't matter from which direction nucleophile going to come in to attack the central carbon, always experience strong repulsion force of this two oxygen. Okay? That's why carbon dioxide is always it's a weak nucleophile. Okay? It's not, weak electrophile. Sorry, this carbon is electrophilic, but it's a weak electrophile because of any nucleophile coming to attack the carbonyl carbon will experience repulsion force of the two oxygen atoms. But anyway, now if you look at the peroxide, it's about 10,000 times more nucleic than phenol. So yeah, it could react with carbon dioxide because this phenol is okay nucleophile, not great, but peroxide is actually a pretty good nucleophile. And although the oxygen atom on the peroxide is more nucleophilic than the ring, that's why when you have alkyl halide react with peroxide, is always O alkylation, always O alkylation. So the oxygen atom is a lot more nucleophilic, okay, than the ring, because negative charge mostly still on oxygen, okay, mostly still on oxygen. However, because the high temperature, the high carbon dioxide pressure, so the reaction actually happen under thermodynamic equilibrium. So although the ring carbons, they are less nucleophilic than the oxygen, but the product, the C oscillation product, like we see here, okay, it's a more stable product because of carbonyl group can directly communicate with the ring. So you have a larger scale of electron delocalization. So the C oscillation product is a lot, the more stable than the O oscillation product. If you think about O oscillation product, I'll just show you what it is. Okay, if if you have the O oscillation product. That's O oscillation product. And as you can see, the carbonyl group cannot communicate with ring pair electron. So you don't have you cannot enjoy the same degree of electron delocalization as you can find in this molecule. Okay? So that's why you form the C oscillation product. You don't see the O oscillation product because the reaction, the high temperature, high pressure lead to thermodynamic control. Okay, but some of you may have noticed, okay, when we have phenol undergo electrophilic aromatic substitution reaction, and this is a electrophilic aromatic substitution for the aromatic ring because carbon dioxide is electrophile here, So this is a EAS reaction, and the negative charged oxygen certainly is OP director, but why we are only showing the O product, O isolation product, not the P isolation product. Okay, why? Okay, we have to look at the the stability. Okay, and if you look at this, compare the C isolation product and the P isolation product. Okay, the C isolation product is sizably more stable than the P isolation product because in this O isolation product you have this intramolecular six-membered hydrogen bonded structure. So this OH group can bond to the this hydrogen bond to this oxygen, give you highly stable six-membered structure, hydrogen bonded structure. So that makes this O isolation product more stable than the C isolation product. Okay. Anyway, so the just give you one more relevant example. So if we have carbon dioxide, say 130, doesn't matter, high pressure. Okay. So the just this one, because high pressure, high temperature lead to thermodynamic equilibrium. So you can have the ring connect to the oh, let's show. Just give you one example of mechanism. So hopefully you guys can have a bit more understanding this whole thing, including something you should have learned in the chapter 13. So basically, this thing gonna come over here, this thing here, here. So this is well, we have then certainly we can, move this around to here. Yeah, we can make this oxygen to take this proton away, and this is gonna come here, and I give you the this one is stabilized by the intramolecular hydrogen bond. And usually, the this kind of reaction often will be followed by a protonation reaction, then give you the O hydroxy benzoic acid. So you have carboxylic acid, carboxyl group, the OH group next to it. So that's usually the final product. So the key part is a high temperature, high pressure of carbon dioxide. You know, we set the reaction system at its equilibrium, so you will get the C substitution product, and this C substitution product is hydroxy carboxylate, and the ortho one is more stable than the parallel one because of the intramolecular hydrogen bond between the hydroxy group and the carboxylate group. All right, then probably we're going to talk about the very last, reaction of the phenol, oxidation of phenols. And we know alcohols can be oxidized, okay, into aldehyde or ketone. If it's primary alcohol, it can be oxidized aldehyde if you pay attention to, the avoiding water. If it's secondary alcohol, it can be oxidized to ketone. And the phenols, actually, they are more easily oxidized than alcohol. And especially 1,2 or 1,4 benzene they can be very easily oxidized into quinols. So what's quinol? We can use in this 1,4 dihydroxy, the benzene diol as example. In the 1,4 benzene diol, we have aromatic ring. We have 2 hydroxy group. Now, if you oxidize, essentially you take these 2 hydrogen away. These 2 hydrogen atoms away. Okay. Then, obviously, if you 2 hydrogen atoms away, you also need to make corresponding rearrangement of electrons. So instead of 2 carbon oxygen single bond, you will get 2 carbon oxygen double bond. And then the aromatic ring here, aromaticity will be lost. You're only going to have the 2 double bonds on the ring, okay, in the ring, but you also going to have 2 carbon oxygen, double bonds. So I just want to emphasize the 4 hydrogens originally on the ring. There's no change on those 2 hydrogens. You're taking away the 2 hydroxy oxygen. And this reaction can be done by many oxidants. One of common one is Jones reagent. That's the chromic acid we used in chapter 16. I assume you used in organic lab as well, right? Do you guys use this Jones reagent? Called Jones reagent, chromic acid. Do you guys use it in lab? Not sure? Just treat a primary alcohol. Anyway, if you didn't use it, it's a big deal, okay? And you also can use the silver oxide as oxidation agent. And the 1,2 benzene diol, same reaction will happen. Again, you take 2 hydrogen away from 2 hydroxy group. At the same time, the 2 CO single bond become 2 CO double bond. And those ring carbons, no real change on them. They just rearrange the electrons. The beauty of such reactions is that the oxidation from the benzene diol 1,2 or 1,4 to its corresponding for quinol, okay, can be done two single electron steps, and the reaction is a highly reversible process. And this kind of basically if you have this 1,2 or 1,4 benzene diol, it has a capacity of giving up to 2 electrons. Okay? If give up 2 electrons, become quinol. Give 1 electron, become this thing. Well, intermediate is a free radical. Okay, and on the same, basically this is a reducing agent. It's a reducing agent. Okay? And the quinol can easily accept 2 electrons, become hydroquinol. This is called 1,4 benzene diol. Okay, there's another name for this guy. Okay, so because of this electron transfer process is highly reversible, so this makes this kind of the hydroquinol or 1,4 1,2 benzene diol. They are the energy storage devices, biological energy storage devices, because of this one can give electron, and this one after giving electron you form quinol, then later can accept the electron. So that's also why those polyphenols often can be have polyphenols. Many of them have the health benefits because of those polyphenols can eliminate those oxidative and harmful radicals from our body because of those polyphenols. Here, this is a polyphenol. This is a polyphenol. Those polyphenols can acting as a reducing agent, so remove those harmful and oxidative free radicals from our body. And one of example, one of kind of molecules, okay, is often found in biological system is called ubiquinol. Ubiquinol is a quinol, and has the basically CO double bond in conjugate with this CC double bond, 2 CC double bond, and another CO double bond. So this guy, can have, can reversibly accept electrons into then it will be reduced into the 1,4 benzene diol structure, and in such a process, energy can be released. Okay, so this energy releasing process, can be used to drive the cellular process. So that's why this ubiquinol is can be found in many places in the cells of biological system, and also why it's called ubiquinol. Ubiquinol means it can be found everywhere. So it's of huge biological importance. Last section of this chapter, we're going to be talking about the spectroscopic features of phenols. So in many aspects, first look at infrared. The infrared spectra of phenols are very similar with alcohols because of we know the alcohols, the most signature feature is that the strong and intense OH band. Usually you can find it around around 32, 3300 reciprocal centimeter. So this is a OH stretching band because OH is a highly polar bond. So it's always its stretching vibration can the absorb infrared photons very intensively. So if you have OH group, you should never miss it. Okay. So phenols also have such OH group. So it also shows a very intense OH stretching band. That's pretty much the same. And you really can't using its the frequency, OH stretching frequency to differentiate phenol and alcohol because of the peak frequency. This one, okay, strongly depends on degree of extent of hydrogen bond. So the exact frequency of this peak, okay, is not a highly reliable way to tell, oh, what kind of OH group I have. Okay, so if you're talking about infrared signature of phenol, OH group of phenol and alcohol, they are the same. Okay, but one major difference between phenol and the alcohol is the CO bond. Okay, CO bond in phenol and alcohol is different. In alcohol, you have sp3 carbon oxygen, okay? And in phenol, you have sp2 carbon oxygen. And this CO bond, CO single bond stretching vibration is different enough. Usually can be used to resolve, can be used to differentiate, the phenols from alcohol. And alcohol, this CO bond stretching vibration usually found somewhere around 1100 reciprocal centimeter. 1100 could be as low as 1050, but basically somewhere, if you look at the CO stretching vibration, is somewhere here, alcohol. Okay, but the phenols, because we have sp2, the CO bond, its stretching vibration frequency is observably higher, not hugely higher, usually around 1200. Okay, so that's a major difference you can see between IR of phenol and IR of alcohol. The other difference is, alcohol, you have an intense sp3 CH peak. Okay, but the phenol, if you don't have in this particular phenol, you have CH3, you still have sp3 CH. Okay, so you see something here. Okay, but if it's just unsubstituted phenol, you won't see anything, at between say 3000 and 2800, you don't see that. So phenol, regular phenol, you don't have sp3 CH vibration, and usually alcohol, you always have sp3 CH, the stretching vibration. That's a major difference between phenol and alcohol. And the proton NMR, really not much to say. Basically, the hydroxy proton phenol, again, the chemical shift value can vary a lot, so you really cannot say much. So the only thing you can say, if you add D2O, you shake. If it disappears, probably you can say, oh, that's hydroxy proton. And the big difference, if you look at proton NMR and the phenol regular alcohol, phenol has a lot of aromatic protons. They have around 7 ppm. But if it's regular alcohol, you don't have aromatic protons. You don't have any peak around 7 ppm. So that's the big difference. And the carbon-13 NMR of phenols, and you have all those aromatic protons. The aromatic aromatic carbons. Aromatic carbon of benzene generally found about 130 ppm, and that's related with double bond. And if you look at phenol carbon-13, the carbon directly connect to O, understandably, has a much higher chemical shift value than the rest of the ring carbons. Okay. Why? Because the oxygen is an electron withdrawing group. If you look at the inductive effect, so that's why this one has the highest chemical shift value. And if you look at rest of ring carbons, you look at something. These two carbons, okay, the chemical shift values are lower than this. Okay? That cannot be explained by inductive effect alone. Because if we explain by inductive effect alone, you would expect this guy, this carbon, of higher chemical shape value than this. But in reality, C is lower, okay? And same thing, the P also lower than the metal. So this one can be just a similar pattern observed, on this compound, okay? So this it can be partially explained, okay? By resonance form of the phenol. What you can see is, the out of the 4 resonance forms, okay, and those 3 shows that oxygen lone pair is donated to the ring. What you can see, the negative charge can be on the carbon also to the hydroxy group or para to the hydroxy group, but it will never be on this carbon. Okay? And the negative charge means the electron density on OP position, they are higher. When the electron density is higher, chemical shift value is lower. Okay, so that explains why you see that these 2 sides, okay, chemical shift value is substantially lower than this side, and because of the metal side, okay, cannot receive the electrons from the resonance effect. So metal side, chemical shift value actually similar with the aromatic ring, benzene, okay, carbon. But the both also in the para, the chemical shift value is substantially lower than the para benzene. UV visible spectroscopy. Well, we one thing we can see is that the phenol, the lambda maxima is sort of similar with benzene, but if some give a slight increase of lambda maxima because of the lone pair, probably reduce the homo-LUMO gap. And if you using a base to remove a proton, you get a phenoxide, you see even greater, the effect on the lambda maxima. You see the lambda maxima move to long wavelength side by 25 and 17, the nanometer respectively. Again, showing that have basic extra lone pair is impact on the homo gap, even smaller. So experimentally, is actually is this property can help us to actually, if you are doing the reaction of phenoxide with the alkyl halide, say if you're doing this reaction, acetone is a solvent in the potassium carbonate. So this is a reaction, often done in a laboratory setting. Okay? So the one way to actually for you to when you're doing this reaction, when you start mixing those things, potassium carbonate, mixing phenol, alkyl halide, potassium carbonate, acetone, then you start to reflect it. You will see the reaction mixture a bit yellowish. The yellowish thing is actually coming from the phenoxide, because the phenol react with potassium carbonate, give you a little bit of phenoxide. And the phenoxide, after whenever you see the alkaline salt, alkaline metal salt, the alkaline metal part is always spectator arc. So the is basically only the phenoxide problem. And phenoxide, because of its absorption, lambda maxima is sizably, the wavelength is sizably longer than the neutral phenol. So its absorption, although it's in the UV part, but its tail, absorption tail, can go into a little bit into visible part. It can give you a little bit of yellowish tint of the solution. Okay? So if the reaction finished, then phenoxide is all consumed. The solution go back to clear. Okay, so that's just one of the ways you can make use of longer lambda maxima of phenoxide compared to phenol. So here basically we concluded chapter 23.